When we look at a kidney stone on a CT scan, we often focus on a single number, the Hounsfield unit, but this only tells us the average density of the stone. It does not tell us what is happening inside it. This is where the concept of the heterogeneity stone index becomes important. Instead of looking at one average value, it looks at how much the density varies inside the stone. A stone with many different densities has a high heterogeneity index. A stone that is uniform throughout has a low one. Micro-CT imaging has helped us understand why this matters. When we look at stones under micro-CT, we see that they are not solid blocks. They are built in concentric layers, almost like the rings of a tree. Each layer has a different mineral composition and therefore a different Hounsfield unit. Some layers are dense and hard, others are softer and more brittle. These layered structures create natural weak zones inside the stone. When shock waves enter such a stone, they do not travel evenly. They reflect, refract, and concentrate stress along the boundaries between these layers. That is where microcracks form, and those cracks are what drive effective fragmentation. This explains an important clinical observation. Two stones can have the same average Hounsfield unit on CT, yet behave very differently during SWL. A homogeneous stone, even if it is not very dense, may resist shock waves because the energy spreads evenly through it. A heterogeneous stone, even if its average density is high, may fragment more easily because the internal layers and interfaces amplify stress. So stone density alone is not enough. What really matters is the internal microstructure of the stone. Modern imaging has shown us that cracks, layers, and mixed composition are what determine how shock waves propagate and where the stone begins to fail. This is why a flexible, adaptive ramping strategy is so important. We are not just matching energy to size or density, we are allowing the shock waves to explore the internal architecture of the stone and exploit its natural weaknesses. Understanding stone heterogeneity is what turns SWL from a mechanical procedure into a truly personalized treatment. These two animations show something very important about how stones respond to shock waves. On the left, you see what happens when a lithotripter has only a few large energy steps during ramping. The energy jumps quickly from low to high. Because of that, the shock waves do not have time to interact with the internal layers of the stone. They hit the stone more like a blunt force. The outer shell may crack, but the deeper layers remain relatively intact. The result is coarse fragmentation, with larger pieces that are harder to pass and more likely to cause obstruction. Now look at the animation on the right. Here, the lithotripter offers many small energy steps as we ramp up toward the maximum level. Each small increase in energy allows a different internal layer of the stone to respond. Softer layers begin to crack first, then slightly harder ones, and gradually the internal structure becomes weakened from the inside out. By the time we reach full treatment energy, the stone is already full of microcracks and separation planes. When high energy is finally applied, the stone breaks into much finer fragments. This is how we exploit the layered morphology of kidney stones. We are not just applying power, we are using controlled, progressive energy to let the shock waves find and open the natural weak zones between layers. The practical message is simple. A lithotripter with many ramping steps gives you more control over how energy interacts with the stone. Systems that provide more than 15 energy steps before reaching the recommended maximum allow a much more precise and biological way of fragmenting stones. That is why ramping resolution matters. More steps do not just mean smoother control. They directly translate into finer fragmentation, better clearance, and better outcomes for the patient.